The universe is a vast ocean with invisible currents. These are the intergalactic winds, and they hold the secret to how star systems are born. By the end of this, you will see the night sky not as a static picture, but as a dynamic masterpiece shaped by forces from beyond our galaxy. How can a wind in the emptiness of space ignite a star? And what does a supermassive black hole have to do with the air you breathe? We are about to trace the journey of the very atoms that make up our world, from a galactic explosion to the cradle of a solar system. What does it mean for our home to be part of such an ancient, interconnected story? Think of the cosmos not as a void, but as a landscape carved by gravity over billions of years. This is the cosmic web, the universe's grand architecture. It is a tapestry of immense filaments, threads of dark matter and gas stretching across the emptiness. Where these threads cross, they knot together into dense clusters, cities of galaxies. And between these great structures lie the truly vast spaces, the cosmic countryside, filled with a thin, searing hot gas. This gas is ancient, a relic from the dawn of time, and it is the raw material for everything to come. It is also the starting point for our intergalactic winds. To grasp their power, we must shift our perspective. The space between galaxies is not a tranquil vacuum. It is an ocean, subject to tides and storms of unimaginable scale. Within the crowded galaxy clusters, titanic events unfold. Galaxies collide, merging in slow, silent dances that unleash torrents of energy. Supermassive black holes at the hearts of galaxies awaken, feasting on matter and belching out colossal jets of radiation and particles. These are the engines that drive the cosmic weather. They heat the surrounding gas to millions of degrees, creating immense pressure. And just like air rushing from a high-pressure system to a low one on Earth, this superheated gas erupts outward. It streams along the filaments of the cosmic web, pouring from the dense clusters into the quieter voids. This is the birth of an intergalactic wind. It is not a breeze of air, but a hurricane of charged particles and raw elemental matter, moving at speeds that can approach a fraction of the speed of light. This wind carries with it the story of cosmic violence, and it is about to write a new chapter somewhere else, in the quiet, dark clouds where stars are waiting to be born. These galactic superwinds begin with a cosmic crisis, a fever of creation so intense it threatens the very galaxy that hosts it. Picture a single galaxy, not in a quiet, steady state, but in the throes of a starburst. This is a period of frantic, almost violent star formation. Thousands, even millions of stars are igniting in a relatively short cosmic time, but this festival of light has a dark side. The most massive of these new stars live fast and die young. Their lives end not with a whisper, but in cataclysmic supernova explosions. Meanwhile, the fierce radiation and stellar winds from all these young stars combine into a constant, searing gale. The galaxy's interior becomes a pressure cooker. The combined energy from countless supernova and stellar winds has nowhere to go but out. It blows a titanic bubble in the galaxy's own gas supply, and then it ruptures. A fountain of superheated, chemically rich gas erupts from the galaxy's core or its star-forming disk. This is the galactic superwind, a tempest of matter streaming out at millions of miles per hour. It is a self-inflicted wound, a process so powerful it can strip a galaxy of the very fuel it needs to make future stars. But in this apparent catastrophe lies a deeper purpose. The gas carried by this superwind is not pristine. It has been processed, Inside those short-lived massive stars and in their violent deaths, nuclear forges created elements far heavier than hydrogen and helium. We are talking about carbon, oxygen, iron, silicon, the very stuff of rocks, of oceans, of living bodies. The superwind acts as a cosmic delivery service. It takes these precious, forged elements and hurls them out of the galactic neighborhood, polluting the void with the seeds of complexity. This means the birth cries of one generation of stars in one corner of the universe are actively preparing the raw materials for an entirely different story to begin somewhere else. The iron in your blood and the calcium in your bones were once part of such a stellar storm, ejected into the darkness to await a new beginning. But the galactic superwind is not the only force capable of launching matter into the great between. An even more violent and fundamental source of intergalactic winds lies at the very hearts of galaxies themselves. This is the realm of the supermassive black hole, not as a silent pit, but as a cosmic engine in its most active, furious state. When such a black hole is actively feeding, pulling in vast clouds of gas and dust, the material does not simply vanish. As it spirals inward at nearly the speed of light, it forms a searing, glowing disk of plasma. This accretion disk becomes one of the brightest objects in the universe, outshining its entire host galaxy. We call this an active galactic nucleus, or when it is exceptionally powerful, a quasar. The energy released is almost beyond comprehension, a continuous explosion that can last for millions of years. And this energy does not just radiate as light. It can organize itself into two narrow, unimaginably powerful beams or jets that erupt from the black hole's poles at nearly the speed of light. These jets can stretch for hundreds of thousands of light years, punching clear through the galaxy and beyond. But alongside these focused beams, the sheer radiation pressure from the quasar's heart can drive a more spherical, yet equally colossal, outflow of gas. This is an Aegean-driven wind. Think of it as a shockwave of pure energy, slamming into the galaxy's reservoir of star-forming gas. The force is so immense it can push that gas right out of the galaxy's gravitational grip, hurling it into intergalactic space at relativistic speeds. For the galaxy itself, this is a profound and sudden transformation. It is effectively robbed of its future fuel. The furious birth of new stars, a process that might have continued for billions of years, is abruptly quenched. The galaxy enters a quiet, mature phase, its stellar population aging without renewal. On the surface, this seems like a story of pure cosmic destruction, a black hole sterilizing its own home. But the narrative is far grander. This violent act of quenching is also a profound act of cosmic regulation. By preventing a single galaxy from greedily using all its gas to create stars too quickly, these Aegean winds help dictate the demographics of the universe. They ensure a diversity of galaxy types, from vibrant, star-forming spirals to quiet, elliptical giants. More crucially for our story, this process is a master distributor. The gas ejected is not lost. It is enriched with heavy elements forged in earlier generations of stars, and now it is being launched on a journey across the cosmic web. The fury of a feeding black hole, therefore, becomes a sculptor on the grandest scale. It takes the complex atoms created within a galaxy and scatters them into the vast intergalactic voids, seeding the darkness with the very ingredients needed for the next chapter of creation. The most destructive force we know becomes, paradoxically, a vital source of raw material for the future. These winds are a chemical archive, a flowing record of cosmic history. To understand what they carry, we must look beyond the simple idea of gas and see them for what they truly are, a rich, complex soup of elements. When astronomers point instruments like the Hubble Space Telescope or the Chandra X-ray Observatory toward these vast outflows, they do not see a blank slate. They detect the distinct spectral fingerprints of oxygen, carbon, silicon, and even iron. These are not the primitive elements born in the Big Bang, hydrogen and helium. These are heavier atoms, forged in the nuclear furnaces of stars and scattered by the violence of supernova. Every atom of oxygen you breathe was once deep inside a massive star that no longer exists. The carbon that forms the backbone of life on Earth was created in a stellar core and then cast out into the void. This is the profound story of recycling written in light across the cosmos. The intergalactic wind is carrying the ashes of dead stars, the processed remains of entire stellar generations across unimaginable distances. Astronomers have a specific term for this. They call it metallicity, which simply means the abundance of elements heavier than hydrogen and helium. It sounds technical, but its meaning is beautifully simple. A high metallicity means the gas is rich with the building blocks of complexity, and this is the wind's most vital gift. When this enriched gas, after its epic journey across the cosmic web, finally begins to cool and condense in a quiet, dark molecular cloud, it does not start from scratch. The seeds of future worlds are already swirling within it. The silicon and iron are there to one day form rocky planets and metallic cores. The carbon and oxygen are present, ready to become mountains, oceans, and atmospheres. Without this delivery of heavy elements from earlier stellar explosions, new star systems would form from only the simplest, lightest gases. They might have stars, but they would lack the raw chemical diversity to ever build a planet like Earth, let alone an asteroid belt or a comet rich with water and organic molecules. So the intergalactic wind is far more than a stream of particles. It is a delivery service for the entire periodic table. It ensures that new stellar nurseries are pre-stocked with the essential ingredients for planets, and by extension, for the potential of chemistry and complexity to arise. This connects us directly to that ancient flow. The iron in your blood, the calcium in your bones, the oxygen filling your lungs right now. Every atom of you that is not hydrogen was once part of such a cosmic journey. It was forged in a star, ejected by a galactic wind, and after eons adrift in the darkness, it found its way into the cloud that collapsed to form our sun and its planetary family. You are, quite literally, made from stardust that was carried across the universe by these invisible currents. The wind shaped not just where our solar system would form, but what it would be made of. Detecting a wind in the emptiness between galaxies seems an impossible task. How do you measure something that is less dense than the best vacuum we can create in a lab, yet stretches across millions of light years? The answer lies not in trying to see the wind itself, but in watching how it alters the light that passes through it. Astronomers turn to the universe's most brilliant lighthouses, quasars. As the intense beam of light from a distant quasar travels across the cosmos toward our telescopes, it passes through these vast, tenuous filaments of wind. The gas in the wind does not let all the light through unscathed. Atoms of specific elements like oxygen or silicon are hungry for very specific colors or wavelengths of that brilliant light. They absorb those precise slices of the quasar's spectrum, leaving behind dark, narrow gaps. Each element creates a unique pattern of gaps, a chemical fingerprint. By analyzing these absorption lines, scientists can perform a kind of cosmic forensics. They can read the wind's composition, determine its temperature, estimate its incredible density, which is still almost nothing by our standards, and crucially, measure its velocity. A shift in the position of these lines tells them whether the wind is rushing toward us or away, and how fast. This is how we first began to map the invisible. But to see the full picture, we need another kind of eye. X-ray observatories like Chandra peer into the hearts of galaxy clusters. There, they detect the faint, diffuse glow of gas heated to millions of degrees, the very engine fuel that drives these colossal outflows. By combining these techniques, the subtle fingerprints from quasar light and the broad glow of hot gas, astronomers transform abstract theory into observable, mappable science. They are tracing the hidden architecture of the cosmic web itself, not with pictures of swirling clouds, but with graphs of missing light and soft X-ray glows, a detective story written in the shadows of the universe's most brilliant beacons. A galaxy is not an island isolated in the void. It is enveloped in its own atmosphere, a vast and diffuse sphere of hot gas known as the galactic halo. This halo is the galaxy's frontier, its first point of contact with the wider cosmos. When an intergalactic wind, born from a distant quasar or a galactic starburst, finally reaches a new galaxy, it does not strike the starry disk directly. It first collides with this immense gaseous envelope. The encounter is a slow cosmic shove, a pressure that builds over millions of years. On the side facing the wind, the halo gas is compressed. You can picture this like the wave that builds up at the bow of a ship as it plows through water, a standing shock front of heated, pressurized gas. This compression has two possible futures. In one scenario, the squeezed gas can cool. As it cools, it grows denser, and pockets of it can begin to condense out of the hot halo, like droplets forming in a cloud. These cooling droplets, now rich with the heavy elements carried by the wind, can then rain down onto the galaxy's star-forming disk below. This is a delivery of fresh, enriched fuel, a gift from the cosmic winds that could spark new waves of stellar birth. But the wind can also act as a thief. If it is particularly strong and relentless, its pressure can overcome the galaxy's gravitational grip. It can begin to scour gas directly from the halo, a process astronomers call ram pressure stripping. It is as if a hurricane were blowing the very atmosphere off a planet. This strips the galaxy of its reservoir of future star-making material. So the galactic halo becomes a dynamic battlefield, a regulator. It is the galaxy's first line of defense against the chaos of intergalactic space, but also its primary intake valve for new resources. The fate of the next generation of stars hinges on this delicate balance between compression and stripping, between receiving a delivery of cosmic ingredients and having your larder blown clean away. This means the story of any new star, including our own sun, did not begin in a quiet, isolated cloud. It began with a negotiation at the galactic edge, a silent, slow-motion struggle between an incoming wind and a protective halo, determining what raw materials would ever get the chance to fall inward and begin the journey toward light. The galaxy's fate depends on the nature of the wind that finds it. While a raging tempest can strip away its future, a softer, more persistent flow can be its salvation. This is the gentle breeze scenario, a cosmic delivery of life-giving fuel. Not every intergalactic wind is born from violence. The cosmic web itself, that vast architecture of filaments, acts as a system of rivers and aqueducts on a universal scale. Along these dark matter threads, vast reservoirs of cooler, denser gas can flow steadily for billions of years. Imagine this not as a hurricane, but as a persistent, nourishing drizzle. This is a cold flow accretion, a continuous trickle of pristine hydrogen and helium from the depths of intergalactic space directly into a waiting galaxy's embrace. In the early universe, this was likely the primary way galaxies grew, sipping directly from the cosmic tap. This gas is primordial, largely untouched by the nuclear forges of earlier stars. It is the universe's original hydrogen fuel, the most basic ingredient for building new suns. When this gentle inflow, perhaps given direction by the broader push of larger-scale winds, finally settles into the calm of a galactic disk, something transformative happens. It mingles with the existing, enriched gas, increasing the overall density of the giant molecular clouds that drift there. Think of a sponge. A dry sponge is light and airy, its fibers barely touching. But add water and it becomes heavy, its structure compressed and dense. That is what this gentle cosmic rain does to a star-forming cloud. By increasing the density, it tips a delicate balance. Inside every cloud, there is a constant struggle between two forces. Outward pressure from heat and turbulence tries to keep the cloud puffed up and stable, while the inward pull of gravity tries to crush it. For a star to be born, gravity must win. When the gentle intergalactic wind adds more material, it makes the cloud heavier and denser. The gravitational pull increases, becoming stronger than the internal pressure that holds the cloud apart. At a certain critical point, a pocket of the cloud can no longer support its own weight. It begins to collapse. This collapse is the first pivotal step in the birth of a star. So, in this quiet narrative, the intergalactic wind is not a destroyer or a regulator, but a midwife. It provides the final, crucial nudge, the extra mass that turns a stable, dark cloud into a stellar nursery, ablaze with new light. It is the breath that whispers to gravity, and gravity listens. This reveals a profound duality in the cosmos. The same mechanism that can quench a galaxy's fire in one place can, with a different character and intensity, be the very spark that ignites it in another. The universe writes its stories not with absolutes, but with balances, where the fate of entire solar systems hangs on the subtle difference between a gale and a breeze. But the gentle breeze is only one side of the story. A galaxy can also find itself sailing directly into a cosmic hurricane, and the consequences are absolute. This is the Gale Force scenario, where the intergalactic wind transforms from a nurturing midwife into a cosmic fire extinguisher. To see this in action, we must look toward the most crowded places in the universe, the dense, ancient clusters of galaxies. Here, hundreds or even thousands of galaxies swarm together like bees in a hive, all embedded in a searing ocean of superheated gas known as the intracluster medium. For a spiral galaxy rich with cool gas, falling into such a cluster is like a sailing ship entering a storm. The galaxy is moving at tremendous speed, and it plows directly into this scorching, dense headwind. The effect is brutal and efficient, a process astronomers call ram pressure stripping. Imagine holding a dandelion seed head out the window of a speeding car. The wind doesn't just ruffle the seeds, it rips them clean away. That is what happens to the galaxy's star-forming fuel. The immense pressure of the onrushing intracluster medium acts like a cosmic sandblaster, scouring the cool, dense gas directly from the galaxy's disk. This gas is the very lifeblood of stellar birth, the raw material for future generations of suns. In a relatively short cosmic time, the galaxy is rendered barren. With its fuel reservoir stripped away, the vibrant cycle of star formation grinds to a halt. The galaxy's character changes forever. Its disk, once shimmering with the brilliant blue light of young, massive stars, slowly begins to fade. Those hot, blue stars have very short lives. As they die out and are not replaced, the dominant light shifts to the longer-lived, cooler, redder stars. The galaxy's color literally shifts from blue to red. Its spiral arms, fed by the dynamic churn of gas, slowly blur and fade as the galaxy's structure relaxes into a smoother, more featureless shape. This is the origin of what astronomers call the red and dead galaxies, the massive elliptical giants that dominate the hearts of dense clusters. They are cosmic retirement homes, filled with an aging population of stars with no new children being born. Their story of vibrant creation ended billions of years ago, abruptly quenched by the environment they entered. So the intergalactic wind, in this ferocious form, becomes a powerful agent of cosmic regulation. It demonstrates with stark clarity that a galaxy's destiny is not written by its internal laws alone. Its fate, its very appearance in our telescopes, is dictated by the neighborhood it lives in and the invisible weather it must endure. The same force that can gently trigger the birth of a star in one quiet corner of the cosmos can, with greater fury, end the story of stellar birth for an entire galaxy in another. This duality is the heart of the narrative, a reminder that creation and quietude are two sides of the same universal process, both guided by the same invisible currents flowing through the dark. The story does not end with the birth of a star. It continues into the cradle of planets, around a newborn sun. A vast, swirling disk of gas and dust takes shape, a protoplanetary disk. This is the construction site for entire solar systems where dust grains collide and stick, growing into pebbles, then rocks, and eventually planets. For a long time, astronomers saw this disk as a closed system, a self-contained nursery where the star provided all the ingredients. But the influence of those vast intergalactic currents may reach even here, into this intimate scene of creation. An influx of material from a passing galactic wind, carrying its unique chemical signature, could gently rain down upon this spinning disk. This is not a catastrophic event, but a subtle addition, like a distant spice merchant adding a rare flavor to a local recipe. The wind might deliver exotic isotopes, forms of elements with slightly different atomic weights, forged in specific types of stellar explosions far away. It could also carry a specific spin or angular momentum, subtly nudging the disk's rotation. The direct impact is incredibly delicate, a whisper against the roar of a young star's energy. Yet, over the thousands of years it takes for planets to coalesce, this external seeding could leave a faint but permanent mark on the resulting worlds. It might alter the temperature profile of the disk's outer regions, changing where ice can form, and thus where giant, gassy planets might take root. More intriguingly, it could directly implant its unique chemistry into the growing planetary bodies. This idea moves from theory toward evidence when we look at some of the oldest objects in our own solar system, meteorites. Certain meteorites, time capsules from the dawn of our planetary system, contain tiny grains with highly unusual isotopic ratios. These ratios do not match what we would expect from the general cloud that formed our sun. They are chemical outliers. The leading explanation is that these grains are literal stardust, pre-solar grains that formed around other, earlier stars and were ejected into space. They then drifted across the interstellar medium, perhaps riding a localized shockwave from a nearby supernova, before finally being incorporated into our own protoplanetary disk as it was taking shape. This supernova blast wave is essentially a small-scale, intense version of the galactic winds we have been discussing. It means the recipe for Earth and its sibling planets was not purely local. Our solar system's pantry was stocked, in part, by ingredients from far-off cosmic kitchens. The iron in Earth's core, the silicon in its crust, even the water in its oceans, might carry within them the faint, isotopic signature of multiple stellar ancestors, delivered by ancient winds that blew through the darkness long before our sun was a spark. These cosmic rivers carry an invisible force, one that shapes their flow in ways we are only beginning to see. Intergalactic space is not a simple emptiness. It is threaded with vast, ghostly magnetic fields, remnants of the universe's earliest moments. They are unimaginably faint, but they are everywhere. When an intergalactic wind begins to move, it does not travel through a passive void. It flows through this magnetic tapestry. The rushing, turbulent gas of the wind grabs hold of these field lines, stretching and twisting them like taffy. This process amplifies the magnetic forces, weaving them into the very fabric of the wind itself. Suddenly, the wind is not just a stream of particles. It becomes a magnetized fluid, and that changes everything. This invisible magnetic skeleton creates a form of pressure all its own. Picture trying to compress a bundle of rubber bands. They push back, resisting the squeeze. Magnetic fields within the wind act in a similar way. As a cloud of gas begins to collapse under its own gravity, dreaming of becoming a star, these internal magnetic fields can provide crucial support. They push outward, propping up the cloud's structure and potentially slowing its collapse. This means magnetic fields can act as a cosmic timer, regulating the pace of star birth. A cloud might simmer for millions of years longer, its magnetic pressure holding gravity at bay before finally fragmenting into stellar nurseries, but the influence goes deeper. These fields also act as cosmic rail tracks for some of the universe's most energetic particles, cosmic rays. These rays, protons and atomic nuclei accelerated to nearly the speed of light, cannot travel in straight lines through a magnetized wind. They spiral along the magnetic field lines, guided by their invisible curves. This magnetic channeling determines where this intense radiation is delivered, which can heat surrounding gas or even influence the chemistry of nascent clouds. The study of this dance, the interplay between magnetic fields and ionized flowing gas, is called magnetohydrodynamics. It is one of the most complex frontiers in modern astrophysics. It tells us that to truly understand how an intergalactic wind sculpts a galaxy or seeds a star, we must learn to see not just the matter it carries, but the invisible magnetic architecture it builds and drags along with it. The wind is not a formless stream. It is a structured, guided force, its hidden magnetic rails subtly directing the fate of everything in its path. This grand movement of matter is part of the universe's ultimate recycling program, a process operating on the largest scales imaginable. We call this the Baryon cycle. Baryons are simply the particles that make up all the ordinary matter you can see and touch, from distant stars to the screen you are looking at now. This cycle is the cosmic story of how this matter flows, changes, and moves between galaxies and the vast spaces between them. It is a story with two main acts, driven by the winds we have been exploring. The first act is ejection. Through the furious power of galactic superwinds and the shock waves from quasars, galaxies expel their own enriched gas back into the cosmic web. This is not waste but a vital release. Astronomers call this process feedback, a self-regulating mechanism where a galaxy's own energetic output limits its future growth. It prevents galaxies from consuming all their fuel too quickly, ensuring the universe does not burn out in a single, brilliant flash. But the story does not end with expulsion. This is where the second act begins, a return journey measured in billions of years. The ejected material, now adrift in the intergalactic medium, begins a long, slow cooling process. Over eons, gravity from dark matter filaments and neighboring galaxies begins to tug at these enriched clouds. They start to flow along the invisible rivers of the cosmic web. Some of this material may fall back onto the very galaxy that ejected it in a much later epoch. Other streams may be captured by a completely different galaxy, drifting in from the void as a gentle rain of new, complex ingredients. This is Accretion, the cosmic gathering of resources. The most sophisticated computer simulations of our universe reveal this process in breathtaking detail. They show galaxies not as static islands, but as dynamic knots in a flowing tapestry. Brilliant fountains of matter erupt from their disks, while delicate filaments of cooler gas spiral inward, feeding them. It is a beautiful, intricate dance of outflow and inflow, a ballet that plays out over timescales longer than human history. In this grand view, the intergalactic wind is more than just a weather pattern. It is the circulatory system of the cosmos itself. Just as your bloodstream carries oxygen and nutrients to every cell in your body, these cosmic currents ensure that no region of the universe is ever truly isolated or starved. They guarantee that the hard-won products of stellar evolution, the heavy elements forged in stellar hearts and supernova blasts, are shared across the vast galactic community. This cycle is the universe's long-term strategy for resource distribution, a way to mix the cosmic pot so that every new generation of stars and planets has a chance to be built from a rich and varied inheritance. Our own solar system is one beneficiary of this ancient, patient economy. The Mice Galaxies offer a breathtaking portrait of cosmic winds in action. This pair of spiral galaxies, officially known as NGC 4676, is caught in a slow gravitational dance. Their long, sweeping tails of stars and gas, resembling the tails of two mice, tell the story of a violent interaction. As the galaxies swing past and through each other, their immense gravity acts like a tidal force, wrenching material from their disks and flinging it out into the darkness. But this is more than a simple gravitational slingshot. The collision compresses vast reservoirs of gas within the galaxies, triggering a firestorm of new star formation. And as we have learned, where you have a burst of massive stars, you soon have a superwind. Hubble's sharp eye reveals this process with stunning clarity. Streaming along those iconic tails are not just ancient stars, but brilliant blue knots of newborn star clusters and vast clouds of hydrogen gas, glowing hot from the energy of the stellar nursery. This is the galactic superwind made visible, a direct pipeline from the heart of a galactic collision out into the intergalactic void. The material in these tails is no longer bound to the merging galaxies. It has been given a one-way ticket out, carrying with it the heavy elements forged in the brief, brilliant lives of those new stars. Over hundreds of millions of years, these streaming plumes will drift farther and farther away. The hot gas will gradually cool, and within these isolated rivers of matter, something new may begin. Dense pockets might collapse under their own gravity, forming globular clusters, those ancient balls of stars that orbit galaxies. In some cases, an entire tail might fragment, giving birth to a new, small dwarf galaxy, a celestial offspring born directly from the ejected remains of its parents. The Mice Galaxies show us that the intergalactic wind is not an abstract force. It is a physical, observable process, a bridge of matter actively being built before our eyes. It demonstrates how a single cosmic event, a galactic merger, can become a factory for distributing enriched gas across the universe, ensuring that even the emptiest spaces are eventually seeded with the potential for new beginnings. Yet for a view of these forces operating on the grandest stage, we must look to a city of galaxies. The Perseus cluster is a titan, one of the most massive objects in our cosmic neighborhood, a sprawling metropolis of hundreds of galaxies bound together by gravity. To our optical telescopes, it is a collection of glowing islands in the dark, but to the Chandra X-ray Observatory, which sees the universe in high-energy light, it reveals its true dynamic nature. Chandra's images show the space between those galaxies is not empty. It is filled with a searing ocean of gas, heated to tens of millions of degrees. And within that glowing plasma, we see something astonishing: vast, delicate ripples and immense, dark bubbles. These are not static features. They are the fingerprints of a heartbeat, a slow, powerful rhythm emanating from the cluster's very core. At the heart of the central, dominant galaxy lies a supermassive black hole, and it is not quiet. It is actively feeding, and with each meal, it unleashes twin jets of energy that blast outward for thousands of light years. These jets inflate gigantic cavities in the hot gas, those dark bubbles seen by Chandra. As they push outward, they send pressure waves rippling through the surrounding medium, like sound waves moving through water. These are literal sound waves in space, but on a scale so immense their note would be a deep B-flat, 57 octaves below middle C, a tone the universe has held for 100 million years. This is the physical manifestation of an AGN-driven wind on a cluster-wide scale. The energy from these waves and bubbles acts as a cosmic heating system, stirring the pot of hot gas and preventing it from ever cooling down enough to fall back into the galaxies. This process is a masterclass in self-regulation, a feedback loop of astonishing precision. If too much gas begins to cool and condense toward the center, it fuels the black hole, making it more active. The black hole then erupts more violently, its winds and jets heating the gas back up, which shuts off the fuel supply. The black hole's activity then subsides until the gas cools again and the cycle repeats. It is a thermostat for an entire cluster, ensuring the central galaxy does not greedily consume all the surrounding resources in a single burst of star formation. The influence of this single central engine, therefore, stretches across millions of light years. It dictates the climate for every galaxy dwelling in that cluster, effectively deciding which will remain star-forming spirals and which will be quenched into passive red ellipticals. The gentle rain of gas that might have nurtured new stellar nurseries in hundreds of galaxies is evaporated by this pervasive intergalactic wind, a demonstration of how the most localized event, a black hole's meal, can shape the destiny of an entire metropolitan region of the cosmos. The early cosmos was a far more turbulent and intimate place. Galaxies were not the well-spaced islands we see today. They were packed closer together, and within them, stars were being born at a frantic, almost reckless pace. This was an era of cosmic adolescence, raw and energetic, where every galactic neighborhood crackled with activity. In such crowded conditions, the influence of intergalactic winds was not a rare event. It was a constant, shaping presence, a form of galactic harassment that left a permanent mark on the universe. Each nearby starburst galaxy was blasting out its own superwind, and each active black hole was driving its own colossal outflow. These winds did not have far to travel before they collided, mingled, and created a chaotic, seething medium between the young galaxies. This intergalactic space was no longer a pristine bath of primordial hydrogen and helium. It was rapidly becoming a polluted, metal-enriched soup. The term metal here, as astronomers use it, means every element heavier than hydrogen and helium. This early enrichment is a crucial piece of the puzzle. It means that stars and planetary systems forming just a few billion years after the Big Bang, a mere fraction of the universe's current age, were already being built from complex ingredients. They did not have to wait for many generations of stars to live and die within their own galaxy. The enriched material was delivered to them, ready-made, by the furious winds of their neighbors. This accelerated the universe's chemical evolution at a breathtaking pace. The cosmos moved from a state of simple, light elements to one rich with the building blocks for rocks, oceans, and atmospheres far faster than we once believed possible. Those first, violent winds did more than just shape individual galaxies. They set the initial conditions for all chemical evolution to come. They primed the entire universe with complexity, laying the foundational groundwork upon which every future stellar system, including our own, would eventually be built. The legacy of that early harassment is written in the oldest stars we can observe, stars whose atmospheres contain the faint but definitive signatures of elements forged not in their own birth clouds, but in the hearts of stars from other, long-vanished galaxies, carried to them on the first great winds of creation. These cosmic currents are too vast and ancient to witness in a single lifetime, so we build digital universes instead. To truly grasp the role of intergalactic winds, we must step into the realm of supercomputers and simulations. This is where theoretical astrophysics becomes a breathtaking visual art. Projects with names like Illustris TNG and EAGLE are not simple animations. They are monumental digital experiments, attempts to encode the known laws of physics into lines of code, and then set a virtual cosmos in motion. Starting from conditions just after the Big Bang, these simulations let gravity work its magic over billions of virtual years. But the magic is in the details. For the simulation to create a universe that looks anything like our own, it must include the messy, complicated physics of feedback. The programmers must tell their virtual particles how to behave when a star explodes, how a black hole's jet carves through gas, and how magnetic fields twist and amplify. They must code in the very winds we have been exploring. Only then, when they hit run, does something remarkable happen. As the simulation unfolds, those intricate filaments of the cosmic web emerge naturally. Galaxies form, evolve, and crucially, they begin to blow bubbles. Fountains of hot, enriched gas erupt from their disks, streaming along the web's invisible highways. The simulation shows that without these winds, the universe looks wrong. Galaxies grow too massive too quickly. They become bloated with stars, and the space between them remains a pristine, empty void. It is only when the winds are switched on, when the feedback loop of creation and expulsion is active, that the virtual universe begins to resemble the one we see through our telescopes. These outflows are not a decorative afterthought. They are the essential pressure valve, the regulatory force that sculpts the cosmic landscape into its familiar, web-like form. Watching these simulations is like having a time machine and a cosmic laboratory combined. Scientists can rewind, fast forward, and change variables. What happens if we make black hole feedback stronger? What if supernovae are less efficient at driving winds? Each experiment reveals how these forces fine-tune galaxy shapes, sizes, and even their chemical makeup. The beautiful, swirling visualizations we see are more than just pretty pictures. They are rigorous predictions, a hypothesis rendered in light and color. Astronomers then take these predictions and compare them to the hard data from Hubble, Chandra, and other observatories. It is a constant conversation between the digital and the observed, each refining our understanding of the other. Through this dialogue, we come to a profound realization. The intergalactic wind is not merely something that happens in the universe. It is a fundamental process that makes the universe look the way it does. Our own galactic home, with its specific size, shape, and chemical history, is one possible outcome from this vast digital library of cosmic potential, shaped by winds that began blowing long before our story even started. But this cosmic story has a complication, a fundamental uncertainty written into the fabric of observation itself. We call this cosmic variance. In essence, it is the possibility that our local corner of the universe, the region we can study in the finest detail, might be unusual. Think of it like trying to understand global climate patterns by only studying the weather in your own backyard. Your experience might be perfectly valid, but it is not the whole story. The strength and impact of intergalactic winds are almost certainly not uniform. They must vary dramatically from one environment to another. In the dense, frenetic heart of a massive galaxy cluster, these winds are likely constant, ferocious gales that ruthlessly strip galaxies bare. But out in the vast, sparsely populated cosmic voids, the winds might be little more than a faint, gentle whisper, a slow drizzle of primordial gas. Our own home, the Milky Way, resides in a relatively quiet suburban neighborhood known as the local group. It is a small collection of galaxies, not a teeming metropolis. The intergalactic weather we experience here is comparatively mild. This presents a profound challenge for astronomers. If we base our entire understanding of these universal processes solely on what we see around us, we risk building a model of cosmic evolution that is incomplete or even misleading. Our local conditions may represent just one chapter in a much longer and more varied book. To move past this limitation, science must cast a wider net. Astronomers cannot rely on a handful of well-studied galaxies. They must survey immense volumes of space, cataloging the properties of millions, even billions, of galaxies across all types of environments. This is where the next generation of observatories enters the story. Instruments like the Vera C. Rubin Observatory, currently under construction in Chile, are designed for this very purpose. Its mission is not to stare deeply at a single object, but to scan the entire southern sky again and again, night after night for a decade. It will detect and measure billions of galaxies, constructing the most detailed three-dimensional map of the cosmic web ever made. Within this vast statistical sample, the subtle and dramatic effects of intergalactic winds will finally be revealed in their full diversity. We will see how they sculpt galaxies in crowded clusters versus isolated fields. We will trace how the chemical enrichment they carry varies from the dense urban cores of the universe to its remote rural outskirts. Only by gathering this enormous census can we begin to distinguish between what is a universal rule of galaxy growth and what is merely a local peculiarity of our own cosmic backyard. The quest to understand these invisible currents, therefore, is also a quest to see beyond our own parochial view, to grasp the true character of the cosmos in all its magnificent and varied complexity. The journey of this ejected gas is a story of cosmic potential, where its ultimate fate is written in its own temperature and density. Like a handful of seeds scattered by the wind, some will find fertile ground, while others simply become part of the soil. The hottest, most diffuse material, blasted out by the most violent events, has a very different destiny than the cooler, denser clumps. For the superheated gas, its journey may be a one-way trip into the void. This material, having been heated to millions of degrees, is so energetic and spread so thin that it cannot easily cool down. It simply expands, merging with the vast, warm, hot intergalactic medium that already fills the filaments of the cosmic web. It becomes part of the background ocean, a permanent addition to the seething plasma that flows between the galaxies. In this form, it may never again coalesce into something new. Its story is one of diffusion, a slow fading into the cosmic background. But not all the wind's cargo is so ephemeral. Within the raging outflow, there are pockets of cooler, denser material. These are the survivors, the clumps that manage to hold together. For them, the story is just beginning. As they travel away from the fury of their birth, they begin to radiate away their heat, slowly cooling over millions of years. As they cool, they contract, growing denser, and with increased density comes increased gravitational pull. These clumps can become self-contained islands adrift in the darkness. We see evidence of this in our own galactic neighborhood. Astronomers detect what they call high-velocity clouds, massive collections of neutral hydrogen hurtling through the halo of the Milky Way. Many of these are believed to be the cooled remnants of ancient galactic winds or intergalactic gas streams, now falling toward our galaxy for the first time. In the profound emptiness between major galaxies, an even more remarkable transformation can occur. If a large enough clump of this enriched gas cools and collapses under its own gravity, it can ignite star formation entirely on its own, far from any parent galaxy. This is the birth of an isolated dwarf galaxy, a faint, diffuse collection of stars born directly from the wreckage of a cosmic storm. These tiny galaxies are the orphans of the intergalactic wind, living testaments to the creative power hidden within what seems like destruction. Perhaps the most poetic fate, however, is a return home. Not all ejected gas escapes the galaxy's gravitational pull forever. Some of it, particularly the material from a galactic superwind, is launched on a great arc. It soars high into the galactic halo, cools, and then, pulled by the persistent tug of the galaxy's gravity, it begins to fall back. This creates a galactic fountain, a beautiful cycle of expulsion and return. Imagine a geyser on a planetary scale. The gas rains back down onto the galactic disk, not in the same place it left, but spread across a wider area. This process completes a local recycling loop, bringing the enriched material, now seasoned by its journey, back to fuel a new, more distributed generation of stars. It is a reminder that even within the grand flows of the cosmic web, there are intimate, local cycles at work. So the intergalactic wind is not merely a force of dispersal. It is a mechanism of distribution, seeding the cosmos with possibilities. Its cargo may become a permanent part of the intergalactic sea, a new and isolated island universe, or a returning nutrient that rejuvenates its own home. Each outcome depends on a simple, physical balance between heat and gravity, a balance that writes countless different endings to the same epic beginning. This history is etched into the stars themselves, a living archive of cosmic events. Galactic archaeology is the science of reading this stellar record, and intergalactic winds are the invisible authors of many of its chapters. The key lies in a star's chemical composition, its unique fingerprint of elements. When a star forms, it locks in the chemical makeup of the gas cloud that birthed it, preserving that moment in time. A star born from pristine, primordial gas will contain almost nothing but hydrogen and helium. But a star born from gas enriched by an earlier wind, carrying the ashes of distant supernova, will be laced with heavier elements like carbon, oxygen, and iron. By measuring these abundances in millions of individual stars, astronomers can perform a kind of celestial genealogy. They can trace stellar families, grouping together stars that share a common chemical heritage and therefore a common birthplace. This allows them to reconstruct ancient events that have long since faded from view. Within the vast stellar population of our Milky Way, galactic archaeologists have discovered something profound. Not all stars share the same chemical story. There are distinct groups of stars whose motion and composition mark them as outsiders, immigrants that joined our galaxy long after it first formed. Their chemical fingerprints do not match the native stars of the Milky Way's main disk. Instead, their signatures point to origins in smaller, satellite galaxies that were torn apart and absorbed by our own over billions of years. This is the fossil evidence of past accretion events, the gentle rain of material from the cosmic web, but the record also shows signs of our galaxy's own violent contributions. The oldest stars in the Milky Way's halo, the sparse outer sphere that surrounds us, show a surprising variety in their metal content. Some are incredibly metal-poor, almost pristine. Others of similar age show slight but distinct enrichment. This suggests that even in the galaxy's chaotic youth, the environment was not uniform. Pockets of gas, freshly polluted by the furious superwinds of the Milky Way's own early starbursts, must have mixed with cooler, pristine inflows. Stars formed in these different pockets carried their distinct histories forward, and we can read them now. So our galaxy's autobiography is not a simple tale of isolated growth. It is a layered narrative of give and take. The Milky Way has been both a recipient, quietly gathering enriched streams from the cosmic web, and a contributor, ejecting its own processed material back into the void through episodes of intense stellar birth and black hole activity. Each major chapter in its life, each merger or period of intense star formation, left a chemical signature in a new generation of stars. By decoding these signatures, we are not just studying astronomy. We are doing cosmic historiography, reading the biography of our galactic home, written atom by atom in the light of its oldest suns. But to grasp the full architecture of this cosmic weather, we must look beyond what we can see. The story of intergalactic winds is inextricably woven with the greatest mystery in modern physics, dark matter. While this enigmatic substance does not feel the push of radiation pressure or the tug of magnetic fields like normal matter, its gravitational influence is the foundation of everything. Picture the cosmic web not as a structure of gas and galaxies, but as a skeleton of invisible mass. Vast halos of dark matter surround every galaxy, acting as immense gravitational anchors. These halos are the primary reason baryonic gas, the ordinary matter that makes up stars and planets, accumulates in the first place. The gas flows along the gravitational contours shaped by dark matter, falling into these deep, unseen wells. In essence, the entire large-scale structure of the universe, the filaments and voids that channel the intergalactic winds, is first drawn in the dark. The winds do not blow randomly. They follow the roads and highways laid down by the gravitational landscape of dark matter. This means the very paths these cosmic currents take, whether they become a gentle stream or a raging river, are dictated by the distribution of something we cannot directly observe. Some theoretical models go a step further, proposing that dark matter itself might have a faint, secondary role in the wind's behavior. If certain types of dark matter particles can interact with each other, annihilating or decaying, they could release small amounts of energy. This energy, injected into the surrounding gas, might provide a subtle, additional source of heating, influencing how the wind cools or expands over cosmic time. While this remains speculative, it highlights a profound link. By meticulously studying the observable effects of intergalactic winds, the way they shape galaxies and distribute elements, astronomers can place indirect constraints on the nature of dark matter itself. The behavior of the visible becomes a clue to the properties of the invisible. Every measurement of a wind's speed, temperature, and chemical content is not just a data point about gas. It is a test, a way of probing the gravitational scaffolding that holds the universe together. The wind, therefore, blows through the realm of both seen and unseen forces, connecting the luminous story of stars and planets to the dark foundation upon which that story is built. The next chapter of this story will be written by a new generation of eyes on the cosmos. To transform our understanding of these cosmic winds from a compelling narrative into precise, quantitative physics, we need instruments capable of dissecting their faint whispers across the spectrum. The journey is just beginning, and the tools for the next great leap are already on the horizon or taking shape. Leading this charge is the James Webb Space Telescope. Its profound infrared sensitivity allows it to do something Hubble cannot: peer directly through the veils of dust that often shroud the most intense regions of star formation and galactic interaction. Webb will watch in unprecedented detail as incoming intergalactic winds compress gas clouds or as outbound superwinds strip them away. It will measure the chemical fingerprints of the gas in these turbulent zones, telling us exactly what elements are being moved and at what stage in the process. But to understand the hottest, most energetic component of these flows, we need to see the universe in X-rays. That is the mission of the Athena Observatory, a groundbreaking mission planned for the 2030s. Athena will not just detect hot gas, it will analyze it with a spectrometer of astonishing power. Think of it as a cosmic speedometer and chemist's lab combined. It will measure the velocity of million-degree winds with a precision never before possible, untangling multiple streams flowing at different speeds. It will determine the exact abundance of elements like oxygen, neon, and iron within those searing outflows, giving us a detailed inventory of what the wind is carrying away. Meanwhile, back on the ground, a new titan is rising. The Extremely Large Telescope, or ELT, in Chile will use a mirror nearly the size of a baseball diamond and revolutionary adaptive optics to cancel out the blurring of Earth's atmosphere. This will give it a view of distant galaxies as sharp as if it were in space. The ELT will map the subtle motions of gas within and around galaxies with exquisite clarity, allowing astronomers to see the direct gravitational and kinematic effects of an incoming wind. They will watch gas clouds being accelerated, spun, or torn apart in real time on a cosmic scale. Together, this suite of observatories represents a holistic approach to a holistic problem. Webb sees the cool, dusty birth and death of stars. Athena diagnoses the superhot plasma driving the system. The ELT maps the detailed kinematics, the motion of everything in between. They will move us from simply detecting that a wind exists to understanding its complete life cycle, its thermodynamics, and its precise cause and effect on galactic evolution. The fuzzy concepts of today will become the hard data of tomorrow. The next decade promises not just more information, but a fundamental revolution in how we perceive cosmic weather. We are about to watch the invisible become visible, not as a blur, but as a finely detailed map of one of the universe's most vital circulatory systems. Our existence is a story of delicate cosmic timing, written by forces far beyond our planet. One profound question emerges from the grand narrative of intergalactic winds. Did these invisible currents, in some essential way, make our presence here possible? The answer lies in a razor-thin balance. If the galactic weather in our neighborhood had been slightly different, the story of Earth might never have been told. Consider a scenario where the wind was a relentless gale. A stronger, more persistent flow from the surrounding cosmic web could have scoured the young Milky Way of its star-forming gas long before our solar system had a chance to coalesce. Our sun would have lacked the raw material to ignite. In the opposite extreme, a universe too calm presents another problem. If the winds had been too gentle or entirely absent, the enrichment of our galactic neighborhood would have been achingly slow. The gas from which our sun and planets formed might have remained pristine, containing only the lightest elements from the Big Bang. Without the steady delivery of heavier atoms like carbon, oxygen, silicon, and iron, carried across space by ancient stellar winds, rocky planets could not have assembled. There would be no terrestrial world, no metallic core to generate a protective magnetic field, no mineral crust, and no chemistry complex enough to lead to life. This leads us to a fascinating philosophical observation, often called the anthropic principle. It suggests that the fundamental conditions of our local universe, including the behavior of intergalactic winds, had to fall within a very narrow, just right range for observers like us to eventually arise. It is a cosmic Goldilocks zone, not for temperature but for galactic environmental factors. The wind in our part of the cosmos could not be too strong nor too weak. It had to be precisely tuned to allow for a galaxy that retained enough gas to form stars, but that gas also had to be sufficiently enriched with the building blocks of complexity. This is not a scientific test or a prediction. It is a reflective lens through which to view our extraordinary place in the cosmos. It forces us to acknowledge that our story is not merely one of biological evolution on a stable planet. It is a story deeply entwined with galactic ecology. The chain of events that led to a thinking species gazing at the stars includes chapters written by quasar outbursts in distant clusters, by supernova in neighboring galaxies, and by the gentle, enriching rain of matter that drifted into the Milky Way over billions of years. Our local cosmic climate was a silent, unseen participant in every step of our genesis. When we look up at the night sky, we are not just looking at points of light. We are witnessing the specific environmental conditions that made our home and ourselves a physical possibility in this vast and ancient universe. Long before telescopes, humanity looked to the sky and felt the wind. It was the breath of the world, an unseen hand that could caress a field or flatten a forest. It is no wonder that cultures across the globe wove this fundamental force into their deepest creation stories. In ancient Greece, the anemoi were the wind gods, each a cardinal direction with a personality, shaping seasons and guiding ships. In Hindu tradition, Vayu is the deity of wind, the very breath of life that animates the cosmos, a vital force present in all living beings. For the Navajo, Nilchai is the holy wind, a sacred power that gives life, thought, and speech, connecting all things. These were not mere weather reports. They were profound recognitions of an invisible, animating power that shaped destiny. They saw wind as a cosmic messenger, a carrier of change, a literal and spiritual breath from the heavens. This ancient, poetic intuition now finds a startling echo in our most advanced science. We have discovered that the myths held a metaphorical truth with a breathtakingly literal counterpart. The universe itself breathes. It exhales colossal winds that carry the seeds of creation across the void. Those stories told around ancient fires of gods breathing life into the world were glimpsing a fundamental process of cosmic ecology. Our modern narrative of galactic superwinds and quasar-driven outflows is in essence the same story told with a new vocabulary, measured in megaparsecs and millions of years instead of human seasons. This connection is more than a charming coincidence. It reveals something fundamental about the human journey to understand our place in the cosmos. We begin with observation, with the feeling of a breeze on our skin, and we build stories to explain its source and power. Those stories, those myths, are the first models of the universe. They are frameworks for asking questions, and sometimes, millennia later, our technology and reason catch up to our imagination, not to erase the old stories, but to fulfill them in ways the storytellers could never have dreamed. The wind that was once the breath of a god is now understood as a river of ionized gas streaming from a feeding black hole. Yet both descriptions point to the same awe-inspiring reality, an invisible, shaping force that governs the birth and death of worlds. This continuity reminds us that science does not strip the universe of wonder, it deepens it. It takes the poetry of our ancestors and shows us that the verse was written in the language of physics all along. Our drive to find meaning in the gust that rustles the leaves is the same drive that points a spectrometer at a distant quasar. We are still listening for the message in the wind, and now we are beginning to understand its words. This ancient metaphor of wind as a life-giving force finds a perfect echo in a simple, earthly scene. Think of a vast, ancient forest. This forest is the cosmic web, its canopy stretching across the entire landscape. Each individual tree, from the mightiest oak to the slender birch, represents a galaxy, a living entity rooted in the soil of dark matter. Now feel the wind moving through this forest. It is never truly still. This wind carries the vital ingredients for the forest's future. It picks up seeds and pollen from a towering pine and carries them across a river to a sunlit clearing. There, with the right conditions, a new sapling takes root. This is the gentle breeze of cosmic accretion, delivering fresh material that allows a new pocket of star formation to ignite within a receptive galaxy. But the same wind can also be a violent storm. A gale of hurricane force might slam into a cluster of trees, snapping major branches or even uprooting an older, weaker tree entirely. The splintered wood and scattered leaves are carried far from their origin, landing in distant parts of the forest. This is the quenching gale of a ram pressure wind or a furious Aegean outburst, stripping a galaxy of its star-forming gas and ejecting its enriched material into the intergalactic void. The health of the entire forest ecosystem depends entirely on these patterns of wind. A section sheltered from storms might grow dense and uniform, while a windy ridge will feature hardy, stunted trees shaped by constant pressure. The nutrients from a fallen giant decay and are spread by the breeze, enriching the soil for the next generation. In this way, a single event in one part of the woods, a tree falling or a fire burning, can influence the composition and growth of life far away, mediated entirely by the moving air. Our cosmic forest operates on the same principles, just over scales so vast our minds can barely hold them. The gentle rain that helped our own galactic tree sprout its spiral branches, and the violent storms that pruned its growth over eons, were all part of this grand, universal weather system. It is a continuous cycle of dispersal and renewal, where the end of one story actively writes the beginning of countless others, all connected by the invisible currents flowing through the dark. The wind between galaxies is nothing like the air moving through a forest. This is the first and most vital correction to our mental picture. On Earth, wind is a fluid dance of countless molecules, constantly bumping and jostling, transferring energy through direct collisions. The atmosphere is thick with them, but intergalactic space is a vacuum so profound it makes the best vacuum chambers in our laboratories seem crowded by comparison. Here, particles are so desperately sparse that a single atom might travel for light years without ever striking another. There are no collisions to speak of, no billowing gusts or turbulent eddies in the traditional sense. So what is actually moving? The answer is a plasma, a sea of ionized gas. This means the atoms have been stripped of their electrons, creating a soup of free charged particles. And charged particles do not need to touch to interact. They communicate across vast distances through invisible electromagnetic fields. The motion of this plasma is a bulk flow, a collective river where the entire stream moves together, guided not by bumping, but by the grand forces of magnetism and gravity. It is less like a terrestrial breeze and more like the entire ocean slowly shifting its course, with currents shaped by planetary rotation and the pull of the moon. To call it a wind is a useful metaphor for its directional movement, but its underlying physics belongs to an entirely different realm. This leads to the second misconception, the idea of a smooth, uniform stream. The reality is far more textured and dynamic. These cosmic outflows are not featureless clouds. They are intricately structured, filled with complex internal weather of their own. Within the broad river of plasma, immense shock waves form where fast-moving material plows into slower, denser regions of the intergalactic medium. These shocks are like cosmic sonic booms, but in a medium where sound cannot travel. They instead heat gas to incredible temperatures and accelerate particles. Furthermore, the flow is not smooth. Observations reveal it is clumpy and filamentary. Denser knots of cooler gas can be embedded within the hotter flow, like lumps of dough swirling in a batter. Magnetic fields, twisted and amplified by the turbulent motion, wrap around these structures, giving them shape and sometimes even holding them together against the forces that would tear them apart. What we label as a single wind is, upon closer inspection, a mosaic of different densities, temperatures, and velocities, all traveling in the same general direction but with a rich internal anatomy. Our final reliance must be on instruments that see the unseen. The majestic spiral arms of a galaxy, glowing in optical light from billions of stars, tell us nothing about the superhot wind screaming out from its core. That wind is completely invisible to telescopes like Hubble when looking in ordinary visible light. To trace these phenomena, we must turn to other windows on the electromagnetic spectrum. X-ray observatories like Chandra are our primary tool. They detect the faint, diffuse glow of gas heated to millions of degrees, the telltale signature of a galactic wind or the hot intracluster medium. Ultraviolet satellites can catch the absorption lines from slightly cooler, flowing gas as it blocks the light of distant quasars. Radio telescopes map the synchrotron radiation emitted by electrons spiraling at near light speed along magnetic field lines within these outflows. Each of these techniques paints a different part of the picture. By combining them, we assemble a composite portrait of something no single eye could ever perceive. Moving beyond the simple, poetic image of a cosmic breeze is not about losing wonder. It is about exchanging a sketch for a masterpiece, where every brushstroke is a precise measurement of temperature, velocity, and composition. The true nature of these winds is more astonishing than any simple analogy, a complex physical process that writes the history of the cosmos in the language of plasma physics and high-energy light. This grand story of cosmic winds is not locked away in an ivory tower. You can reach out and touch it, becoming an active participant in this discovery. The tools of modern astrophysics are increasingly open to anyone with an internet connection and a spark of curiosity. Platforms like NAS, a universe of learning, offer a portal into this research, providing interactive visualizations that let you manipulate the variables of a galactic simulation. With a few clicks, you can watch what happens when you increase the strength of a supermassive black hole's jet or dial down the efficiency of supernova feedback. You can see in real time how these changes alter the fate of a virtual galaxy, watching its star formation flicker and fade or its gas erupt in a brilliant fountain. This hands-on exploration transforms abstract theory into an intuitive understanding, letting you feel the delicate balance of forces that govern the cosmos. Beyond simulations, you can contribute directly to the cataloging of the real universe. For over a decade, projects like Galaxy Zoo have harnessed the power of human pattern recognition, something computers still struggle with. Volunteers from around the world have classified millions of galaxies from telescope surveys, looking for subtle details in their shapes. Your eyes might spot the faint, distorted plume of a tidal tail, the telltale sign of a galactic merger that likely triggered a massive wind. You could flag a galaxy with an unusually bright core, hinting at an active black hole that might be driving an outflow. Every classification is a data point that helps astronomers build statistical maps of cosmic phenomena. The peculiar galaxy you identify today could become the target for tomorrow's observation with the James Webb Space Telescope, a perfect laboratory for studying the intricate details of an intergalactic wind in action. This is the beautiful democratization of astrophysics. The quest to map the invisible currents of the universe is no longer the sole domain of a small group of specialists with access to giant telescopes. It is a collaborative, global effort. By engaging with these citizen science platforms, you join a community of hundreds of thousands of people who are collectively helping to sift through the vast data of the cosmos. Your curiosity becomes a valuable instrument, scanning the digital sky for the clues that will refine our models and challenge our assumptions. You are not just learning about these cosmic winds, you are helping to trace their paths and measure their influence. In a very real sense, you become part of the story, adding your own observation to the ancient and ongoing narrative of how the universe shapes itself, one galaxy and one curious mind at a time. The fate of a cosmic wind is decided by a fundamental physical conversation, a dialogue between heat and light. This is the thermodynamics of creation, where the potential for new stars lives or dies in the balance of temperature. When a stream of intergalactic gas slams into a galactic halo or collides with another cloud, it does not simply merge, it creates a shock front, a standing wall of incredible pressure. Think of it as the cosmic equivalent of a sonic boom, but for an entire river of matter. At this shock boundary, the gas is violently compressed, and according to a basic law of physics, when you squeeze a gas, its temperature soars. This newly heated material now holds enormous internal pressure, like the steam in a tightly sealed kettle. That pressure pushes outward, fiercely resisting any further collapse. For gravity to win and begin pulling this gas into a dense core that can ignite a star, that heat must escape. The gas must cool. Cooling in the near vacuum of space is a subtle and specific art. It happens not through contact with cooler air, but through radiation. Atoms within the hot gas, excited by collisions, must find a way to release their pent-up energy. They do this by emitting light at very specific wavelengths, like microscopic beacons blinking in the dark. The most efficient radiators are atoms of heavier elements like oxygen, carbon, nitrogen, and iron. Each time one of these atoms emits a photon of light, it sheds a tiny bit of the cloud's thermal energy. This process, line emission, is the universe's primary coolant. It is how a seething cloud sheds its heat and becomes capable of collapse. The presence of these heavier atoms, delivered by the wind itself, is therefore not just a chemical detail. It is the essential thermostat for star formation. A wind carrying only pristine hydrogen and helium would struggle to cool efficiently at all. Its story might end right there, as a perpetually hot, puffed-up cloud forever held apart by its own internal pressure. But the cosmos has another, even more potent cooling agent: interstellar dust. These are microscopic grains of carbon and silicate, essentially soot and sand, forged in the atmospheres of aging stars and scattered by their deaths. If a galactic wind has swept up such dust grains from its journey, the cooling game changes dramatically. Dust grains have a vast surface area relative to their size, and they are brilliant at absorbing heat and re-radiating it away as infrared light. A dusty cloud can cool orders of magnitude faster than a dust-free one. It is the difference between trying to cool a hot pie by waiting for the air to steal its heat versus plunging it into a snowbank. The dust acts as that snowbank, providing countless surfaces for the energy to bleed away. This rapid cooling allows gravity to take hold quickly before turbulence or other forces can disrupt the fragile process. So the fertility of a wind-borne cloud, its potential to become a stellar nursery, depends critically on its chemical maturity. Has it been enriched not only with cooling atoms, but with the solid seeds of dust? The legacy of previous stellar generations directly enables the next. This sets the stage for a delicate and continuous battle, a tug of war operating in every promising pocket of gas across the cosmos. On one side, you have the forces of heating, the shock from the wind's initial impact, the continual compression as gravity begins its work, perhaps even background radiation from nearby stars or a distant quasar. These inputs constantly pump thermal energy into the cloud, increasing its outward pressure. Opposing this is the quiet, persistent work of cooling, the faint glow of oxygen atoms releasing an ultraviolet photon. The infrared whisper from a blanket of dust grains. For a star to be born, cooling must outpace heating, even if just for a critical moment. It must allow the cloud's internal pressure to drop so that gravity's relentless inward pull can finally overcome it. This is the hidden threshold. A cloud may be massive, it may be rich with material, but if it cannot shed heat faster than it gains it, it will remain forever in a state of equilibrium, a diffuse and stable cloud. It is barred from becoming a star. The intergalactic wind, therefore, does not just deliver raw material. It delivers a system with a preset cooling capacity. Its history determines its thermal destiny. In this way, the microscopic physics of atom and dust grain emission lines writes the fate of galaxies, directing where light will blossom in the darkness and where it will remain forever potential, locked in a hot, radiant haze. This simple fact changes everything about our cosmic story. We are not just observers of the universe, we are time travelers. The light from that distant, wind-blown galaxy 10 billion light-years away is a 10 billion-year-old message. When our telescopes capture it, we are not seeing that galaxy as it is today. We are witnessing a snapshot from the universe's youth, a moment when it was only a fraction of its current age. The furious superwind we detect streaming from its core, the brilliant shock waves from its quasars are not happening now. They are ancient history, events that concluded eons before our sun even flickered into existence. This delay is the ultimate key to understanding our own origins. The consequences of those ancient storms did not vanish. They unfolded across the ages. The heavy elements ejected by that long-dead galactic tempest spent billions of years adrift, cooling and flowing along the filaments of the cosmic web. The shock wave that compressed a neighboring gas cloud may have triggered a burst of star formation that itself faded into red giants and white dwarfs long ago. The entire cascade of cause and effect, set in motion by winds from the cosmic dawn, has been playing out in slow motion for the entire lifespan of the universe. Our local galactic neighborhood, the Milky Way and its quiet companions, is not a separate entity. It is the present-day product of that ancient weather. The specific mix of elements in our solar system, the very fact that our galaxy has the right amount of gas to have formed stars at a steady pace, these are legacies written by winds that blew when the cosmos was young and turbulent. By pointing our most powerful instruments at the most distant, faintest galaxies, we are not merely cataloging far-off objects. We are performing archaeology on a cosmic climate. We are digging through layers of time to find the root causes of the universe we inhabit. Each spectrum of light from a primordial quasar is a core sample, revealing the temperature, composition, and motion of the intergalactic medium from a specific epoch. We can trace how the enrichment of the cosmos evolved, from the first polluted winds of the earliest galaxies to the more refined outflows of mature systems like our own. This turns astronomy into a historical science. We are reconstructing the environmental conditions that made galaxies like the Milky Way possible. We are asking what the cosmic weather report was 10 billion years ago in a certain region of space, and then tracing how that forecast resulted in the galactic ecosystems we see around us today. The gentle breeze that eventually nourished our own galactic disk began as a hurricane in a different place and time, a force so remote its light is only reaching us now. Our existence here is the long echo of a storm that raged at the dawn of creation. The rocks that fall from the sky are time capsules, and they tell a story of our solar system's windy conception. While we cannot point to a specific intergalactic gust that shaped our sun's birth, the chemistry locked inside certain meteorites whispers of a dramatic, seasoned past. These ancient stones, some older than the Earth itself, contain microscopic grains of stardust that did not form in our solar system. Their isotopic signatures are alien, matching the unique nuclear recipes of specific stellar deaths, like those from red giants or certain supernova. How did these foreign grains become part of the cloud that collapsed to form our sun and planets? The most compelling explanation is a localized, furious wind. A nearby supernova in its final cataclysm would have blasted a shockwave through the surrounding interstellar medium. This shockwave is a hyper-intense, focused version of the galactic winds we have discussed. It would have acted as a cosmic broom, sweeping up these pre-solar grains and hurling them forward, injecting them directly into our own calm, waiting cloud of gas and dust. This means the protosolar nebula was not a pristine, isolated bubble. It was a mingling place. It contained not just the generic gas of the Milky Way's spiral arm, but also the specific, enriched ashes of other stars that had lived and died in our galactic neighborhood. The supernova's shock did more than just deliver ingredients. The sudden compression from that blast wave could have been the final trigger, the critical nudge that caused our particular cloud to lose its balance and begin the gravitational collapse that led to our sun. So the evidence is not in a grand galactic structure, but in the atomic architecture of a stone. When scientists hold a meteorite containing these pre-solar grains, they are holding a piece of that ancient stellar storm. It is a physical fragment of the very wind that both seeded and possibly sparked our entire solar system. This transforms our origin from a quiet, local event into a community affair. We are the product of a galactic environment that was chemically and dynamically connected, where the death of one star set the stage for the birth of another, with our planetary home as the ultimate result. The memory of that turbulent, windy past is not lost. It is preserved in the very bedrock of our cosmic identity, waiting in the asteroids to be read by anyone curious enough to look. The universe's ledger appears to be out of balance. When cosmologists tally up all the normal matter they can see in galaxies, stars, and glowing gas clouds, the numbers do not add up. A staggering amount is simply missing. This is the missing Baryon problem, one of the most persistent puzzles in modern science. According to our most precise measurements of the Big Bang's afterglow, the cosmic microwave background, we know exactly how much ordinary matter, or baryons, the universe should contain. Yet our best surveys of the nearby cosmos can only account for about half of that expected total. Where did the rest go? The leading suspect is not in some exotic, hidden dimension, but in the very winds we have been exploring. Scientists believe a vast reservoir of this missing matter exists in the form of the warm, hot intergalactic medium, often called the WHIM. This is a seething, diffuse ocean of gas threaded throughout the cosmic web, heated to temperatures between 100,000 and 10 million degrees. It is too hot to glow brightly in visible light, yet too cool to shine prominently in X-rays, making it incredibly difficult to detect. This is where intergalactic winds play a dual role. They are both the creators and the custodians of this hidden stockpile. The furious outflows from galaxies and quasars do not just eject matter, they stir and heat it, injecting enormous energy into these vast filaments. This constant agitation prevents the gas from ever cooling down enough to collapse into visible structures like galaxies or cool clouds. The winds, in essence, keep the universe's baryonic savings account locked in a hot, diffuse state, hiding it in plain sight. To solve the missing Baryon puzzle is to complete the cosmic inventory. It is a fundamental accounting exercise for all of existence. By meticulously mapping the dynamics of these winds, tracing their velocity, temperature, and distribution, astronomers are conducting a forensic audit of the cosmos. They are following the energy trails left by ancient outflows to pinpoint where this warm, hot gas should be concentrated. The hunt involves looking for the faintest signatures, the subtle absorption lines in the spectra of distant quasars as their light passes through these filaments, or the extremely soft X-ray glow that might emanate from the densest knots. Each detection is like finding a single receipt from a universe-sized transaction, slowly proving that the matter was never truly lost, just transformed and displaced by the relentless weather of intergalactic space. Unlocking this mystery would do more than just balance the books. It would validate our entire understanding of cosmic evolution from the Big Bang to the present, confirming that the story of matter is one of continuous transformation, not disappearance. It turns the study of galactic winds from a niche topic into a central tool for solving one of cosmology's grandest challenges. This perspective is not just information, it is a lens that reframes our entire existence. To know that the iron in our blood was forged in a star that died before our planet formed, that the very air we breathe was scattered across light years by a galactic wind, collapses the distance between the human scale and the cosmic. We are not separate from the universe we observe. We are a temporary, conscious arrangement of its most ancient materials, a way for the cosmos to know itself. This realization carries a quiet but powerful ethical weight. It moves the story from what happened to what it means for how we live. Our planet is not a stage set against a backdrop of stars. It is an active participant, a fragile oasis shaped by and continuing within these relentless cycles. The same cosmic processes that delivered the water to our oceans and the carbon to our biology are indifferent to our survival. A nearby supernova, a shift in the galactic environment, these are forces beyond our control. This is not a cause for fear, but for clarity. It highlights that the stability we depend on, the thin envelope of atmosphere, the delicate balance of our climate, is a precious and local phenomenon. It is our only home in a vast and dynamic system that operates on timescales of deep time, where entire galaxies are born and die. This cosmic perspective naturally cultivates a profound sense of stewardship. If our world is a rare and intricate product of a 14 billion-year journey, then our responsibility to protect its habitability becomes a chapter in that grand narrative. Caring for Earth's ecosystems, preserving its capacity to nurture life, is no longer just a political or social issue. It becomes an act of cosmic significance, a way of honoring the extraordinary chain of events that led to a living, thinking world. It fosters a humility that is both grounding and unifying. Our divisions, our conflicts, our fleeting concerns are all set against the backdrop of a universe in motion. We share a common origin story written in the atoms of every person, every creature, every rock and river. This knowledge invites a shift from a mindset of ownership to one of belonging. We do not own this planet. We belong to a lineage that stretches back to the first stars, and we hold this world in trust for the future twists of that story. Astronomy, therefore, ceases to be a remote science of distant points of light. It becomes the study of our deepest ancestry. Every telescope image, every spectrum of a galactic wind is a page in our own family history. To look up at the night sky with this understanding is to feel a connection that transcends time and space. We are the universe momentarily awake and looking back at itself with the unique privilege and burden of choice. The future of this small, vibrant world in the stream of cosmic weather is now, for this brief moment, in our hands. The frontier of this research is alive with questions, each one a doorway to a deeper layer of understanding. We have mapped the broad strokes of these cosmic currents, but the fine details remain elusive, hidden in the complex physics of the invisible. For instance, how exactly do the magnetic fields woven into these winds influence their long-term impact? We know they provide structure and pressure, but do they also channel energy in ways that preferentially heat certain regions of a galaxy, subtly guiding where stars can and cannot form? Another major puzzle is efficiency. When a wind scatters heavy elements across the void, how thoroughly does it mix this cosmic pollution into the pristine gas of the intergalactic medium? Is it a gentle stirring that creates a uniform enrichment, or does it leave behind a patchwork of chemically distinct regions, like oil and water not fully blended? This matters immensely for predicting the chemical starting point of future galaxies. Then there are the smallest contributors. We focus on the titanic outflows from massive galaxies and brilliant quasars, but what about the faint, persistent breezes from countless dwarf galaxies? Their individual contributions might be tiny, but their combined effect over billions of years could be the steady drizzle that fills the cosmic reservoirs, a background hum of enrichment that has been overlooked. Perhaps the most tantalizing goal is to witness the beginning of the cycle directly. Can we finally catch a clear, unambiguous image of cold gas streaming from the cosmic web and raining onto a waiting galaxy? Seeing this cold flow accretion in action would be like watching the roots of a tree drink from an underground river, completing our picture of the cosmic ecosystem. Answering these questions will not come from a single telescope or a solitary theory. It demands a symphony of observation. The path forward lies in international collaboration, where data from colossal radio arrays tracing neutral hydrogen, space telescopes dissecting ultraviolet and X-ray light, and ground-based optical giants measuring precise motions are all woven together. We must combine the sharpest images with the most detailed supercomputer simulations, each refining the other. The aim is nothing less than a revolution in perspective, to move from the static snapshots we have now to a dynamic, full-length movie of galactic life. We need to see a galaxy not as a single portrait, but as an entity that breathes, interacts, and evolves in constant dialogue with the winds that shape it. This is the grand challenge. The mystery of the intergalactic winds is not a puzzle we are close to boxing up and putting away. It is a living inquiry, one that grows richer and more intricate with every new discovery, promising to redefine our place in the flow of cosmic time. The story of the cosmos is written in these invisible currents, from the furious outflows of quasars to the gentle rain of cosmic filaments. Intergalactic winds stand as the great sculptors of the cosmic landscape. They are the fundamental architects quietly governing the birth, life, and death of galaxies. They deliver the very elements for planets and, in their diffuse heat, conceal the universe's own missing matter. Our journey has revealed a profound truth that the space between stars and galaxies is not a static void. It is a dynamic highway, a circulatory system for the cosmos, alive with motion and consequence. As we forge new tools to probe these unseen rivers, from next-generation telescopes to vast digital simulations, we draw closer to understanding the complete story of our own origins. Every piece of the puzzle, from the chemistry of a meteorite to the color of a distant galaxy cluster, fits into this grand narrative of flow and feedback. So the next time you find yourself looking up at the stars, remember you are not just seeing points of light. You are witnessing the aftermath. You are seeing the legacy of winds that have blown for billions of years, shaping everything from the grandest spiral galaxy to the atom in your next breath. If this exploration of cosmic mysteries has captivated you, consider subscribing for more journeys to the frontiers of space. We would love to hear your thoughts on these shaping winds in the comments below.